Hello, my name is Cameron Perrie,
And my name is Kristen Twigg.
and over the summer of 2018, we began a project to develop our own flapping wing aerial vehicle with a unique set of morphing wings.
We conducted and continue to work at the University of Maryland College Park through the first year Innovation and Research Experience Program with the Autonomous Unmanned Systems stream, under the mentorship of Derek Yao.
Our main objective is to develop a flapping wing aerial vehicle with the unique morphing wing capabilities.
To accomplish this, we are developing prototype flapping wing air vehicles, then introducing a way to change its flight pattern by morphing the wings and/or tail. This is accomplished by tilting the axis that the wings are flapping on.
We will collect data on how our morphing mechanism affects the prototype control through a series of grounded force tests on it. Before constructing this morphing mechanism, we can simulate our design with MATLAB to analyze its capabilities. This gives us data on the shape, position, and forces of the wings for every degree of variability. The first prototype used parts of other RC vehicles. At this point, we did not have a simulation, but instead used designs for the transmission and wings from an RC bird we bought off Amazon. The electronics of the first prototype were mostly siphoned from an RC helicopter we had. The mechanics we needed to build a solid first prototype only required these simple electronics for a motor, two servos, and radio communications, which were conveniently built into the helicopter board. The X-Wing flight style resembles the flight style of certain insects. It's a clapped fling style of flying that's efficient for smaller vehicles with low Reynolds numbers. Before we started morphing the wings, we used a simple way to control the flapping wing aerial vehicle for flight testing by manipulating the tail. The tail worked to an extent, but was unable to do any complete flight tests because our flapping wing air vehicle grew to be too heavy, gaining pendulum-like momentum and spiraling out of control into the ground. Our bird was just too fat to fly. After attempting to reduce weight and optimize the center of mass of the bird, we realized that the transmission and wings were not powerful enough to support the electronics, aspirations, and available materials. To do this, we decided to move on to a new prototype generation, a larger system capable of supporting more weight.
This new generation has a half-meter wingspan with a standard bird-like two-wing flight style. The image shows the left wing and a wing template. The template allows for ease of wing construction and consistency between every model. We have implemented a larger wingspan for more wing area, causing more lift to carry more weight. The present transmission design is 3D printed for adaptability, durability, and replaceability. We can make modifications quickly using CAD software and print new parts with ease. The gears furthest from the motor are the wing gears and are held in place by flange collars. The left wing gear has a flange collar on it, and another flange collar is needed to be added to secure the right wing gear. The wing gear is held onto a shaft of the transmission via the flange collar. The bearing is in the transmission frame, allowing the shaft to spin freely and turn the wing gear assembly.
A MATLAB simulation is being developed to simulate the 4-bar linkage of the gears to wings. The simulation displays a red circle as the wing gear. This is the first linkage, and the blue lines as the linkage between the wing gear and the wing joints, being the second linkage. The joints' motion on the magenta circle demonstrate the range of the wings. This is the third linkage. The wings are the 4th bar in the linkage, and are not yet in the simulation, although they are pseudo-simulated by these two orange bars flapping. The simulation is still in progress. As mentioned, the 4th linkage, the wing, still needs to be added. Further development would lead to programming the simulation in a 3-dimensional environment, depicting a scene closer to the real version of our 4-bar linkage.
We can then simulate our morphing strategies. This means tilting the linkage to see the effects on the XYZ positions of the wings, and finally add it to the physical prototype if data appears favorable. On top of adding the morphing strategies, a tail and electronic system will also need to be developed and integrated onto the bird for a full working prototype.
We will also incorporate an analysis and prediction of the forces on each section of the wing in the simulation, with data acquired from the load cell sensor apparatus on the grounded prototype. This simulation allows us to quickly view the effects of modifications to the flapping wing aerial vehicle before changing anything physically on the bird itself. Thus, it becomes a more efficient way to further develop and refine the project.
In the scope of the project, we expanded our target from a small, modified, out-of-the-box project to our own custom-developed flapping-wing aerial vehicle with an in-depth simulation.